Good afternoon, everybody. My name is Victor LESKO. I am a second-year PhD student at Laboratoire Hubert. And my talk is about the additive manufacturing of soft magnetic materials. This work happens in the frame of a project founded by the Région Auvergne-Rhône-Alpes, and we have many partners. Nowadays, embedded electronics are everywhere, and most of the components are made from magnetic materials. We can find these magnetic materials for the components of power electronics and as well in telecommunications. If we take the example of power electronics, if we are interested in the inductors, the 3D shaping of the magnetic materials allows to get higher inductances value and lower losses in the material. But in telecommunications, if we are interested in some device as circulators or isolators, the magnetic materials can be deposited only where it is necessary, and it allows to have lighter components with a smaller volume, and they are also cheaper, and also the resolution of the selective laser melting process is better than the mechanical machining. We are more focused regarding the microwave frequency range. We are interested in the ferrite granates because they are excellent. They have excellent properties in this frequency range because they have a high electrical resistivity. The eddy current losses are lower at high frequencies, and as it is also a soft magnetic materials, the hysteresis losses are low. As you can see on the picture, the crystal structure of the YIG, which is iron yttrium granate, is a very complex structure, and it can be easily modified when it interacts with lasers. There are two main goals in this thesis. The first one is the development of a selective laser melting process, which means for YIG powder, which means find the good parameters in order to keep the good properties, the good magnetic properties of YIG, and as well keeping a good mechanical properties. We want to make demonstrators like circulators and isolators for microwave applications. The other main goal is using spatial shaping of the beam and associate it with a wise scanning strategy in order to control the dynamics of the temperature field in the powder bed. So now let's talk more about selective laser melting. It's in the family of powder bed processes because we are directly melting a powder layer thanks to a laser source, rather than putting locally some material. This is a typical setup for selective laser melting. It can be divided into three main steps, which are repeated unless the part is completely built. The first step consists in spreading one layer of powder. Then the layer is scanned by the laser beam, and the powder is melted selectively. And finally, the build platform is lowered, and another layer of powder is spread, etc., etc. And at the end of the process, the powder which has not been irradiated by the laser beam is not melted, and it is removed, and the part is made from the melted powder. It's a relatively quick additive manufacturing process with a good resolution compared to some mechanical machining, for example. These are the parameters which are involved in the selective laser melting process. It is dependent on the laser power, the height of the powder layer, the space between two laser lines, it's called the hatch spacing also, and the scanning speed. And the scan strategy is important too, but more on a mechanical point of view. At this time, we don't have the powder bed setup. We are using this setup, which is made from a galvanometric scanner, and we are using an yttrium fiber laser in the infrared to melt our powder. And as we don't have the powder bed system, we are using a suspension of YIG powder into ethanol. Then we take this suspension with a pipette, and we drop this suspension on our substrate. The ethanol evaporates, and only a thin layer of powder is remaining. These are the previous results which have been published on YIG. The Raman analysis, many parameters have been tested, and the Raman analysis shows that for low laser power, there is the occurrence of a hematite phase in the sample, and for higher laser power, there is a phase transition into magnetic phase. And also it was reported that the sample was destroyed after 10 layers because of residual stresses. And the other figure shows that the sample is still magnetic after the SLM process. And this is to show that we try to find the best parameters for the SLM. And we vary the power, the speed, and the frequency. These are the results we got. And this is a square of YIG of 1 millimeter height. And this is a coplanar isolator. This is, we made some thermal modeling. Also. This is a simulation for a silica glass sample, but it can also work with our powder. And this shows that we can reach a temperature step by doing multibeam processing. And we can also do some preheating, and the temperature step allows to avoid a peak temperature. Okay, to conclude, embedded electronics are everywhere, and the components are more efficient in 3D. And also it allows to make lighter and cheaper components. The SLM is the most suitable additive manufacturing process. But it is difficult to set up because of the complex structure of our material. And also, we show the feasibility of using multi-beam process to avoid, for example, annealing or long time post-processing. Thank you. Maybe I can answer a question.